5.3 is about inverse functions. We're running out of time, and it's not required by the math department, so we're not going to cover it. It doesn't tell you anything that implicit differentiation doesn't tell you, so it's not that important. But we do need to cover 5.4 through 5.7 to some extent, as much as we can. 5.4 and 5.5 are related. 5.4 is about the exponential function with base e. Um, 5.5 is about all exponential and log functions with different bases, not e. So this is the function we want to study in this section, y equals e to the x. We want to know, yes, exactly. We want to know how to derive this guy, how to integrate this guy, how to graph this guy, how to do anything with this guy. The way that e to the x is defined is that the function y equals e to the x is the inverse of the natural log function. So this is the same as solving the equation x equals ln of y. Now, that probably means nothing to you. So let me make it be a little bit more. E to the x and ln x are inverse functions. That's what this is. What that means about their graphs, to give you a good picture to go by here, do you remember what the graph of ln x looks like? Natural log of x? Goes through, what's the x-intercept? 1, 0. And then it's concave up or down? Concave down, because it's bending downward. It's got an asymptote at 0. And it's always going up. It's always increasing. So this is ln. What if I wanted another point on here? When x is e, what does ln give you? 1. Right? We can find e to be the number that makes ln equal to 1. And in case you don't recall, e is approximately 2.72. So the fact that e to the x is the inverse function to ln x means that everything about x and y switches. Right? E to the x is the same thing as if you switch the roles. See how y is equal to ln x here? If you switch x and y, that's the same thing as e to the x. So what that means is to graph e to the x, you can switch x and y. So for example, 1, 0 will become 0, 1. E1 will become 1e. 2, 3. So here's e is about between 2 and 3, 2.7. So here's 1e, 0, 1. And then I'm going to draw you a wrong graph. This is the wrong graph. It's close. It's wrong. Why is that wrong? Yeah, all of a sudden I went below the x-axis here when this guy approaches the y-axis. So everything about x and y switches. Meaning if this guy approaches the y-axis, this guy has to approach the x-axis. So I kind of came close, but not correct. So e to the x has a horizontal asymptote here. So there's kind of a picture for you of e to the x. Concave up, always increasing, horizontal asymptote at 0. The other thing you're going to need to know is, well, the inverse properties. I'll do some examples after this, but inverse properties about how ln and e fight. Right, so if you have natural log of e to the x, what should that equal? X. Right, that's how inverse functions work. The whole point of an inverse function is that it gets rid of the other function. And it goes the other way too. If you have e to the ln of x, you get back what you started with. All right. So let me do some review examples. You should be able to graph a quick sketch of any e function. Right, so if I want you to graph y equals 1 minus 2e to the x, what would you do?
Flip it down to the x one.
So this is your e to the x graph. E to the x always looks like this forever. All I'm doing is adding 1 to that and then multiplying by -2. Right, so you have two things to account for, this multiplication by -2 and this +1. So what's the multiplication by -2 going to do to your e to the x graph? So multiplication by 2 stretches it. Multiplication by negative flips it. Right? So e to the x was right here, 0, 1, 1e. This was my original. When I multiply it by -2, it's going to get flipped down and stretched. So instead of being at 0, 1, what's it going to be at? 0, -2. Because your y values are all getting multiplied by -2. And instead of being at 1e, it's going to be way down at 1, -2e. That's just this part. What's the +1 do? Shifts it which way?
Up.
Up. So then for your final graph, you have to go up. So instead of having horizontal asymptote at 0, your final graph would have a horizontal asymptote at y equals 1. Come through like so it would have points like 0, -1, and 1, -2e plus 1. So hopefully you vaguely remember that. This is basically just transformations, but what I really do want you to remember is the general shape of e to the x. Right? If you can remember this general shape, then you can move it all over the place with a bunch of different transformations. So that's one thing I'd like you guys to have is a picture of e to the x in your head. The other thing you have to be able to do is solve equations. This is more pre-powered. You solve each equation. Have you solved something like 5 e to the x equals 36? So now you're trying to isolate x, right? You know this. You know that ln will kill e and give you back x, give you back the exponent. But the ln doesn't kill the e until it can get right next to it, so you have to get rid of this 5 first. So to solve this, you would start by dividing by 5. e to the x equals 36 over 5. Then to get rid of the e, last it with a natural log. So then natural log of e cancels, leaving you with x equals ln of 36 over 5. Or I have an approximation. I prefer exact, but if you need an approximation, you plug in your calculator, you should get this. If you cannot get that out of your calculator, come talk to me so we can figure out how to use your calculator. What do you think? Easy? You remember that? What if I gave you 5 over 1 plus e to the 3x equals 2? How do you solve hand?
Multiply both sides by 1 plus e.
So you got to get rid of the denominator. We hate denominators. Killed our mother. So we get rid of it. 1 plus e to the 3x. 1 plus e to the 3x. Gone. Gone. So 5 equals 2 times 1 plus e to the 3x. That's an e. Now what do you do? Yeah, so eventually you want to get rid of the e by natural logging, but before you can do that, you have to isolate it. So one method would be to get rid of this 2 by dividing. 5 halves equals 1 plus e to the 3x. Then subtract the 1 over. Right, we're peeling it away to get the e isolated. 5 halves minus 1, 3 halves equals e to the 3x. Then you can get rid of the e by taking the natural log of both sides. By the way, don't please ever write, don't write this. Don't put the natural log over here just because you can't fit it in. Right? If you put the natural log on the right, it just looks stupid, right? Because natural log is supposed to eat something. And in this country, it always comes after the ln. So don't look foolish, put it here. And then the e and the ln cancel, leaving you with what? 3x equals ln of 3 halves. Divide by 3. You have your x isolated. 0.135. So do your, multiply and divide, add and subtract until you have the e isolated, and then on both sides. What if I give you an ln to start with? Like natural log of x plus 2 equals 2. How do you solve this? Yeah, so it's not quite multiplying, but to get rid of an ln, you exponentiate. So if you want to get rid of ln, you can put a base e down here, an exponential function base e. And then put an exponential function base e over here. As long as you do it to both sides, it's perfectly legit. These guys fight. x plus 2 equals e squared. Right, this is an exponent now. The 2 becomes an exponent. So then subtract the 2, x equals e squared minus 2. Whatever that is. 5. So if you start with an ln, isolate the natural log and then e both sides. If you start with an e, isolate the e and then ln both sides. Okay. All right. Let's do some calculus. E to the x is our favorite, absolute favorite calculus function. There is no better function than e to the x. And why? So let's find the derivative of e to the x. The only thing we know about e to the x is that it's the inverse of natural log. Normally we write the natural log function like this, but because e to the x is the inverse of natural log, I have to switch x and y. Because I know how to take the derivative of natural log, I can figure out the derivative of e to the x. So I'm going to work with this equation because I know something about natural log. So this is kind of how you come up with the derivative of e to the x. Start here. And take the derivative with respect to x on both sides, implicit differentiation, d dx, d dx. What happens when you take the derivative with respect to x of x? 1. There's no question about that. If these match, derivative will be 1. Now this side's a little more confusing because you have to take the derivative with respect to x of natural log y. So these don't match now. But you know the derivative of natural log. What happens with natural log? 1 over whatever's inside. Times, because the inside function is more complicated, you have to multiply by the derivative. You have to chain rule. Times dy dx. Right? That's how implicit differentiation works. You do the derivative of the outside, but then you multiply by dy dx for the derivative of the inside. So then if I solve for dy dx, dy dx equals y. So this function, which is e to the x, right? Y equals e to the x. The derivative is equal to the original function. That's what this is saying. The derivative equals the original. Or, if you plug back in, because we started with the assumption that y is equal to e to the x, we get e to the x back. So when you do the derivative of e to the x, you just get the slope of this guy is equal to the y value of this guy. Right, on your graph, if you know the y value, you know the slope. So for example, here's e to the x. What's this point? What's the y-intercept? 0, 1, right? So e of 0 is equal to 1. What's the slope here? 1. The slope of the tangent line is 1. This point up here, 1 comma e. The slope of the tangent line at 1 comma e is going to be what? E. The slope's equal to the y value. So the slope will be 2.7, or e. So every point on this graph, the structure of the graph says that if you want the slope, it's the same as the y. Which means we can do an integral too. Pretty quickly. What's the integral of e to the x dx? E to the x again, plus a constant this time. Right? If the derivative is e to the x, then when you go backward and do the integral, you e to the x. So what this section consists of is first a little bit of review about what this function is, but then you do a bunch of derivatives and integrals that involve u, which you would hope are not very complicated, but turns out you can make just about anything complicated if you try. So let's do some practice. Find the derivative of each function. Y equals 5e to the x. That's y prime. 5e to the x. Because this 5 is a constant multiple. So constant multiples just follow along, and the derivative of e to the x is e to the x. What about if I wrote y equals e to the 5x? I put the 5 inside. What's that do? Y prime will equal
5 here.
Yeah, so the derivative of e to the 5x is e to the 5x again, but because our inside function is more complicated, right, our inside function has a derivative of 5. So the chain rule says multiply by 5. So 5e to the 5x would be the derivative of this. So be careful, if that exponent is more complicated than just x, you have a chain rule. Come down here. Y equals e to the x squared. The derivative of e to the x squared is just e to the x squared again, but then chain rule. Chain rule tells you have to do the derivative of x squared, which is 2x. So y prime will equal 2x e to the x. What do you think? Easy? Hard? Easy. Good. Good, I agree. Let's see if we can make it not easy. So, x e to the 10x is my function. I want the derivative. It's got to be product rule, right? Because you have multiplication. How come I didn't use product rule here even though I had multiplication? Constant. Oh, good. You guys didn't know that like a short 2 months ago. No. How you know that? All right, so I have to do product rule because I have a function times a function. Derivative of the first times the second plus the first times the derivative of the second. How do you do the derivative of e to the 10x?
E to the 10x.
Chain rule, right? Derivative of e to the 10x is e to the 10x, but then the chain rule says you multiply by 10. All right, so the product rule, we use the product rule formula first. Derivative of x is 1, e to the 10x stays the same, x stays the same, but then when we get to the derivative of e to the 10x, we have a chain rule to apply, which is why this 10 pops out. I would probably factor this because it's got an e to the 10x in both terms, so you can rewrite it like this. Right, e to the 10x pops out front, and then you have 1 left here, you have 10x left here. I guess it's not really interesting. What about e to the 5 over x squared? How are you going to do this derivative?
5 times x to the negative 2.
Yeah, I would bring, because this x squared is in the denominator, I'd bring that up and make it 5x to the negative 2. Then your chain rule is going to be no problem. But I'm anticipating a chain rule here because I know I'm going to have to do derivative of the inside. And it'll be easier to do that if I have it written as a negative exponent. So the chain rule says the derivative of e to the 5x to the negative 2 is e to the 5x to the negative 2 times what? Negative 10x to the negative 3. Clean that up a little bit, I guess. X cubed goes to the bottom. And the negative exponents come down again, but otherwise it's whoa, calm down, we ain't doing the integrals yet.
I'm just saying that's something
Oh, don't worry, there's going to be plenty of substitution for you. I know. I wouldn't want to disappoint you. Alright, so let me give you one more derivative. Y equals natural log of e to the x cubed over 1 plus e to the x squared. Derive this bad boy. What should we do?
1 plus ax squared over
1 x squared over here.
What, like 1 over x? And
Oh, right. So the derivative of natural log says you do 1 over whatever's inside times the derivative of the inside. Is that what you guys want to do? What do you want to do instead?
separate.
Use your log rule. Absolutely use your log rule so you can avoid the quotient rule inside. So whenever possible, use log rules first. Right? Because if I separate this division, I can change it to subtraction on the outside. Like this. In fact, natural log of e to the x cubed, I can even simplify further. What's this? X cubed. I like x cubed, I can derive x cubed. So now that I've done some simplification, the derivative looks a little bit easier. This guy's going to become 3x squared. Minus, okay, so now we'll use our natural log rule. The way you do derivatives of natural log is you put 1 over whatever's inside. But but then you have to multiply by the derivative of the inside. So the derivative of natural log is 1 over whatever's inside times, what's the derivative of e to the x squared? E to the x squared again. But you have it inside. Times the derivative of x squared, which is so you get 3x squared minus, all of this is on top. So 2x e to the x squared over 1 plus e to the x squared. These e to the x squareds cancel? Choo choo.
No.
Someone say yes. I was joking. They don't. Why don't these cancel?
The addition.
Because of the plus, right? How's that one? Easy? Hard? Good? Not bad? Terrible? Decent. Decent. I guess I see why you guys don't answer them, because no matter what answer you give me, I'm going to do the same thing. Let's see, that's a good question. So I'll give you one more, and then we can move on to integrals. So let's do, I'm going to do a new one. Natural log of sine of e to the secant of x squared. Oh. You can do any derivative. Integrals you have to be careful making up. When you make up integrals, you run into trouble. But derivatives, we can do it. So how do we do this derivative? 1 over whatever's inside. So 1 over sine of e to the secant x squared, which is actually cosine, but we'll get to that later, times the derivative of the inside. So our first inside function is sine. The derivative of sine is cosine. Rewrite the inside. Times the derivative of e to the secant x squared, which is e to the secant x squared again, times the derivative of secant x squared. What's the derivative of secant? Secant tangent, they all shout. Secant x squared tan x squared times the derivative of x squared. You still have another inside function. 2x. Oh my. Ooh, cosine over sine, I like that. I'm going to do that. I'm going to simplify that. Cosine over sine is cotangent of e to the secant x squared times e to the secant x squared times secant x squared tan x squared. And then I'll probably put the 2x over here. Just to mess with it. Cool? Totally. So the only thing new is the derivative of e to the x and e to the x. If there's something more complicated inside, chain rule. Chain rule, chain rule, chain rule. So let me go the other way. Find each indefinite interval. Let's start the same way. What if I want the integral of 5 e e to the x dx. So this 5 is a constant multiple, which means when you do the integral, you can just let it tag along. And then the integral of e to the x is just like the derivative of e to the x. It's the same thing. Integral of e to the x is e to the x. Oops. But since it's an indefinite integral, I get a plus c. Okay, so the integral of e to the x is just e to the x. This is a constant multiple, so it tags along. It's different, however, if I put the 5 up here. Now what happens? It's going to be a 1/5. The integral, so you might think that the integral of e to the 5x is just e to the 5x again. And you would be partially right. But if you check, it doesn't work out, right? Because the derivative of e to the 5x is 5e to the 5x. Right? So to make up for that 5 you get out of the chain rule, you put a 1/5 when you integrate. False constant. If that 1/5 doesn't make sense, you have to do this with u substitution. U equals 5x. So du equals 5 dx. So you make up for the 5 in front of the dx by putting a 1/5 out front. That's where this is coming. So if it's just a constant multiple times x, when you do the integral, you can divide by the constant. However, what about this? Oh, by the way, you guys know that e to the x quantity squared is not the same thing as e to the x squared, right? Right? E to the x quantity squared means e to the x times e to the x, which when you add the exponents becomes e to the 2x. That's different than e to the x squared, right? So if you don't see these parentheses, assume that the square is on the x. So our square is on the x here. How does that help me? What integration technique can I use? Yeah, how'd you get that? Yeah, so the relationship is that x squared, if you take the derivative, you almost get x. So there's a u substitution relationship here. U is x squared, du is 2x dx. Since you're missing the 2, you put it in. Right? You're missing this 2 in front of the x, but then you make up for it with 1/2. Right, so with this u substitution, your integral becomes 1/2 integral of all of this is du. And then what's left is e to the u. The integral of e to the u is e to the u. So you put your u back in. Okay. Pause. I like it. What if I take this x out? What if I gave you this? How do you feel about that? Don't know what to do with that. That's a good answer. That's a good answer. This guy does not have an indefinite integral that can be written as any function you know. This guy's not integrable. You're not without infinite sums. So this x here, if you put anything other than x, or like a constant times x inside of here, you're going to have to make up for it with a derivative. Otherwise the integral won't be possible. So this guy's not expressible in terms of any functions that you've studied.
What would it be?
They made up a function who's equal to this. It's called the EarthC function. But after you do calc 2, you can express this as an infinite sum, and then you can integrate the sum. But, this integral is used in calculating the probability of the normal distribution. If you ever take a probability of statistics class, the normal distribution is the bell curve. This integral of Feiner's probability. But in a probability and statistics class, this integral is calculated for you to certain decimal places. It's always approximated. You don't actually have some computer approximating. But let me give you some more integrals we can do. Ooh. Integral of e to the x root 1 minus e to the x. U sub. U sub? What's your U substitution?
1 minus e to the x.
Yeah. So if you let u equal 1 minus e to the x, because the derivative of e to the x is e to the x again, you get negative e to the x here. So you almost have your du in there, except you're going to need to multiply by a negative, right? To get the exact du, you have to put a negative in front here, which means you get a negative outside. And then this becomes. So this is negative integral of the purple's du, and then left over is root u. Root u. Which is u to the 1/2. Which is u to the 3/2 over 3/2 when you apply your power rule. Negative 1 minus e to the x when you put your u back in. Up to the 3/2. 3/2 came up as 2/3 just to look prettier. So if you have two e to the x's being multiplied in some fashion, you might be able to pull off a u substitution, right? With u equal to one of the e to the x's. Okay. Two more. 1 over x squared divided by x cubed. Aw, oh man, damn. So how do we do this guy? U is x to the negative 2. Do you guys all see that? Quickly, hopefully. This guy's your u. Because if you do the derivative of him, you get negative 2x to the negative 3. This is your x to the negative 3 sitting in there. Right, so du is equal to negative 2 over x cubed dx. We have the over x cubed portion, we need the negative 2 portion. So you put a negative 2 up top, which gives you a negative 1/2 outside. And then this guy here is du. This guy up here, 1 over x squared, that's x to the negative 2, that's u. Your x to the negative 2. So this becomes negative 1/2 integral. All the blue stuff is du. But then, other than that, we have e to I know the integral of e to the u, d to the u again. So altogether I get negative 1/2 e to the 1 over x squared. Easy? Hard? Questions? That was a sentence. So a lot of these come down to recognizing the right substitution. Because I can't just give you the integral of e to the x, that's too easy. So I have to disguise it with a bunch of other garbage in there. So I have one more disguise. This one's pretty well hidden. Oh, and it's example E. Ha ha ha. I like it. So example E is the integral of 1 over 1 plus e to the negative x dx. There's a couple ways to do this one, but the way I prefer is to use u substitution, but I want to make it a good u substitution first. So for example, if I wanted to make 1 plus e to the negative x equal to my u, what would I need? What's the derivative of e to the negative x? Negative e to the negative x, right? Derivative of x e to the x. So if I wanted to make a u that had an e to the x in it, I would need an e to the x up top. So, one trick you can use is to multiply the top and bottom by e to the x. Right, you can change this integral by doing this. I mean, it doesn't actually change the integral, but it makes it look different. Right, I've only multiplied by 1, so I haven't changed anything. But on top, I have e to the x now, which is good for u substitution. And what do I have on bottom? When I distribute this, what happens? 1 times e to the x is e to the x. What's e to the x times e to the negative x? E to the 0, which is
One, sorry, 1.
So e to the negative x times e to the x, you add the exponents and you get e to the 0. But then anything to the 0 is equal to 1. So over here I'll have plus 1. Now we're cooking. Now we have a u and a du. Now I can let u equal e to the x plus 1, and du will equal e to the x. Right, the derivative of e to the x. So up here, I have du. And down here, I have u. So this becomes the integral of du over u. Which is what?
Natural log, absolute value.
Natural log absolute value of u plus c. Let me stick my u back in. E to the x plus 1. So there's a trick to remember. I don't know, e to the negative x's in the denominator lend themselves well to this trick because when you multiply e to the negative x by e to the x, it cancels it. So that allows you to put your du on top. So if I gave you this integral instead, 1 over 1 plus e to the 2x dx. Do you know how you could do this? So it's almost the same format, so think the same way. Multiply by what though? So you want to multiply by something that's going to simultaneously cancel this out and give you a du on top. So I would do e to the negative 2x and e to the negative 2x. That way you get the integral of e to the negative 2x. When you multiply it and you distribute on the bottom, what happens? The 1 gives you e to the negative 2x, but the e to the negative 2x and the e to the positive 2x becomes 1. So then what would you let u equal? Let u equal e to the negative 2x plus 1. Because the derivative of u is equal to negative 2e to the negative 2x. So I almost have du in there, right? Du would be equal to negative 2e to the negative 2x dx. So I have e to the negative 2x dx. I need an extra negative 2. So I put it in. So this becomes the negative 1/2 times the integral of du right? All of this is on top is du over. So this will be negative 1/2 ln absolute value u plus c, negative 1/2 ln of e to the negative 2x plus 1. So this format here, we have constant, constant, and then e to the x. You can usually multiply by the same thing on top and bottom to make it integrable. All right. So that's the trickiest, I think, the trickiest integral in this section. That's it. That's 5.4. Derivative of e to the x e to the x, integral of e to the x e to the x. So,
Other what?
bases.
Bases.
So in 5.5, we do everything we've already done again, except we do it with other bases. So we want to look at things like this. So a to the x for any number a that's not equal to 0 or 1. It actually has to be bigger than 0 and not equal to 1. So we want to look at these two functions, which are, of course, inverses of one another. So what's the graph of a to the x look like? Any idea? Well, depending on what a is, it's going to change, right? But suppose a is bigger than 1. And a to the x has the same shape as e to the x. For example, if you plug in 0 here, anything to the 0 is 1. So you know a to the x has a 0, 1 intercept. And if you plug in 1, you get out whatever a is. So this is kind of your general function graph for a to the x, as long as a is greater than 1. Do you know what happens if a is less than 1? Nothing. You die. If a is less than 1, then when you plug in 1, you get out a fraction. So the graph ends up looking like this. If a is between 0 and 1, you look like this. Where your y-intercept is the same, but now when you plug in 1, you get out a number less than 1. So it's going down. So pretty much everything you do with e to the x, you can do with you can do with general base a. What would the corresponding log function look like? So the log function, log base a of x, is going to be the inverse to this function, and what inverses do are switch the roles of x and y. So instead of having 0, 1, you're going to have 1, 0. And instead of having 1a, you're going to have a1. And it's going to look something like So same as ln, basically. Right? The only real difference is a stretch or shrink. Okay, but it's still increasing, still concave down. But instead of going through e comma 1, you go through the base, whatever the a is, comma 1. Over here it looks a little funnier, I guess, but you can use the same principle. Because log is the inverse, instead of going through 0, 1, you go through 1, 0. And you go through a comma 1, but a is less than 1. So a comma 1 will be up here. So it looks something like. So, quick review example. If I wanted you to graph y equals log base 2 of x minus 1, what would you do? All right, so log base 2 is different than ln. ln is log base e. Right, if I write log base e like this, which is stupid, nobody writes this, but if I wrote this, this would equal natural log. So what we're saying now is, well, what if we change this e to a 2? What does that do? So what should log base 2 look like? Here's your key to everything. It goes through 1, 0, but instead of going through E1, it goes through 2, 1. It's even better. It's easy. So the graph of log base 2 goes through 1, 0, 2, 1. Vertical asymptote 0. But I didn't ask you for the graph of log base 2, I asked you for the graph of log base 2 of x minus 1. So what's that minus 1 do? Do 1 to the positive because it's inside the function, so it's a horizontal shift. So basically I'm going to take my asymptote, which was at x equals 0, and move it 1 over. So my new graph, let me draw it on a different axis so it doesn't put it all. My new graph, my old graph had an asymptote at x equals 0, right here, vertical asymptote. My new graph, because I'm shifting over 1, has an asymptote at x equals 1. Because I'm shifting over 1, 1, 0 moves to 2, 0, and 2, 1 moves to 3. 1. Log base 2 of x. So these shapes stay the same. The only difference is you have a second point that's a little different. You have a stretch or shrink. So instead of being at 1e, you'd be at 1a. Instead of being at a1 or e1, you'd be at a1. So this point changes, giving you your stretch or shrink. What about equations? What if I wanted you to solve log base 2 of x plus 3 equals 6? The Before, to get rid of a natural log, we would hit it with an e, right? Exponentiate both sides, base e. Because e and natural log fight, hate each other. So to get rid of a log base 2, what do you think you do? 2it. Right? If you exponentiate both sides with base 2, the 2 and the log base 2 inverses, so they cancel, leaving you with x plus 3 equals 2 to the 6th. 64. So to get rid of log base A, log base 2, log base 5, log base whatever, you use the exponential function with the same base. So if this were log base 5, you'd put 5 on both sides as your base. Well, what if I wanted to just solve this? 5 to the x minus 3 plus 2 equals 8. So this is an exponential equation, right? Because it's got the x and the exponent.
Mm-hmm.
So how are you going to isolate x here? Yeah, you gotta isolate. If you're trying to get to x, you have to isolate this guy first. So that 2's got to come over. Now, you kind of have two routes here. You can either apply log base 5 to both sides, or you can apply natural log to both sides. What happens, because this is base 5, you might be thinking, okay, well, let's apply log base 5, which is a good idea. So what happens if we have both sides with log base 5? What's log base 5 of 5 to the x minus 3? X minus 3 cancels, right? On this side, you're left with log base 5 of 6. Add the 3. So this is x. Log base 5 of 6 plus 3. Unfortunately, depending on the calculator you have, you might not be able to enter this in to get an approximation. Some calculators only have base 10 and base e. So, if you have a calculator that doesn't have log base 5, that doesn't let you use any base, then you either need to go back up here and use natural log, or use your change of base formula. Remember your change of base formula? Nope. Log base b of m is equal to any log in the world. Let's use ln. ln of m over ln of b. So because, it just depends. Some calculators will do it, some won't. But if you wanted to calculate, for example, if you wanted to approximate log base 5 and 6, and you don't have a log base 5 in your calculator, you would do natural log of 6 over natural log of 5. Although, what do you, hold on a second, I want to make sure you remember. So, this guy I can't actually evaluate exactly because I don't know what power I have to raise 5 to get 6. So do you remember how logs, a little more basically, if I just want you to evaluate a log like log base 2 of 8, do you remember how to do this? So this is asking what power do you raise 2 to get 8? So you change this into the equation 2 to what equals 8. That's the exponential form. And then you know the answer to this is 3. So this log base 2 of 8 is equal to 3. Right, over here, what I was saying is I don't know what power I have to raise 5 to get 6, right? 6 isn't a nice power problem. So I need an approximation. But if you have a nice power of the base, you don't need an approximation. Just mess around. Log base 7 of root 7? 1/2. What power do you raise 7 to get a square root of 7? You have to raise it to the 1/2 power if the square root is 1/2. So we're not going to do a whole bunch with these actually. Once you get into calculus, E and ln are so nice that you pretty much use them for everything. But in case you're dealing with something else, I assigned some review problems. Go through them and bug me if you can't figure it. But let me give you the calculus of the section. I'll start it and then we'll have to finish it up next. The calculus all relates back to E and ln. Okay, so for the calculus of these new functions, which have a, right, we want to worry about a to the x and log base a of x. Basically, you need these formulas. A to the x is equal to e to the x times ln a. Do you know why this is true? What can you do with multiplication outside of a log? If you multiply by a single number outside of the log, your log rule says you can bring it up top, right? So this x can come up top. And this becomes e to the ln a to the x, and e to the ln cancel, leaving you with a to the x. So e to the x times ln a is another way of writing a to the x. So that being said, what do you think the derivative of a to the x should be? Where a is some constant bigger than 0 but not equal to 1. Well, doing the derivative of a to the x should be the same as doing the derivative of e to the x times ln a. How do you do this derivative? ln a is just a constant. What's the derivative of e to the x?
E to the x.
So the derivative of e to the x ln a is e to the x ln a, but then times the derivative of the inside, ln a, right? Because this is just x times a constant. So the x goes to 1 and the constant stays. But this guy, e to the x ln a is equal to
Yes.
a to the x. So your formula says this. If you want to derive some number to the x where it's not e as the base, it's almost like e to the x. The derivative is almost like the derivative of e to the x. It's almost the same thing, except you get this constant of ln a popping out. So the derivative of a to the x is ln a times a to the x. For logs, you use this identity. Log base a of x is equal to ln x divided by ln a. This is the change of base rule, one form of the change of base rule, the one I just wrote over there. So if you want to do the derivative of a log that's not ln, log base a, it's the same thing as doing the derivative of ln x over ln a. But a is a constant. It's not changing in any particular problem. So all I really have to do is the derivative of ln x. What's the derivative of ln x? What's the derivative of ln? 1 over whatever's inside, right? So 1 over x. What happens with this ln a on the bottom? Tags along. It's constant. It's constant multiple. So you'll have an ln a in the bottom. So when you derive log base a, again, it's very similar to ln x. You're going to get 1 over x. But because you don't have exactly ln, you get an error factor, ln a, popping into the bottom. That's basically the calculus of this section. Right, each of these have corresponding integral facts. Well, the integral fact over here isn't as cool. Or something similar to that. But this guy has a cool integral fact. What should the integral of a to the x be? If you want to integrate just a to the x, you should almost get a to the x again. Yeah, but it's going to have to be divided by ln a. Right, because if you derive a to the x, you get this ln a popping out, so this will cancel it. Let me do a couple of examples. And I'll finish this up next. Find the derivative of each function. So y equals 3 to the x. What's the derivative? Any exponential function, right, when the x is in the exponent, by the way, don't tell me 3 to the x minus 1 over x minus 1. It's garbage, okay? I'll probably fail you if I see you write that. So, why is this not true?
Because we have other stuff.
Because this rule works if you have a constant exponent. Right? If you have x to a constant, where the variable is the base and the exponent is the constant, then you can do the power rule.
Not cheap.
But now my variable is the exponent, so I'm in a whole different realm. But I have a formula, right? Y prime is equal to almost the same exact thing. The derivative of an exponential function is almost the same exact thing. But you have a constant that you have to fix it up with. So the derivative of 3 to the x is ln 3 times 3 to the x. Derivative of 4 to the 7x. Couple things to watch out for here. Derivative of an exponential function is almost the same thing. So the derivative of 4 to the 7x is almost 4 to the 7x, but you need a natural log out front. So you put natural log of 4. Right, that's applying this rule. But But you also have a chain rule to apply, because the inside function is not just x, it's 7x. So then you times by 7. So y prime is 7 ln 4 times 4 to the 7th.
Are you gonna want us to calculate 7 ln 4 or just?
Nah, just leave it. Just leave it. 5 to the sine x derivative. Yeah, so almost exactly the same thing, right? Copy down 5 to the sine x again, but then you need to fix it up with an ln 5. Because the base is different than e. Is there more?
Yes.
Chain rule, right? Derivative of the inside, derivative of sine. So y prime is ln 5 times cos x times 5 to the sine x. So what about log? I'm going to change now logs for a second. Y equals log base 2 of x. So when you're doing the derivative of log, you think of ln. Right? The derivative of ln is 1 over x. So this guy is going to be 1 over x, except you have to fix it up. So on the bottom, you get a factor of ln 2, because the base is 2. All right, last one. Y equals log base 3 of the fourth root of 5x plus 2. I want to find the derivative. I would use my log rule first. Probably save me at least a little bit of time. A little bit of ink, for sure. So, this fourth root can be written as 1/4 power. Right? And all your log rules that you have for ln apply to log base 3, or log base a in general. So the 1/4 comes down. That's just rewriting. I haven't actually done a derivative yet. Now when I do the derivative, what's going to happen? One-fourth is a constant multiple, so he stays out front. Then to do the derivative of log base 3, yeah, so the derivative of log is 1 over x, but because it's log base, it's not 1 over x, it's 1 over whatever's inside. 1 over 5x plus 2. But because it's log base 3, you have to get an ln 3. Chain rule, right? Times the derivative of the inside. So to do log, you do 1 over whatever's inside. Since it's not ln, you put a factor of ln 3. But then chain rule says do the derivative of the inside, which is 5. So altogether, you should get 5 over 4 ln 3 times 5x plus 2. So, a couple things. One, pretty much I've taught you everything there is to teach in this section, except one other thing which is new and I have to show you because you won't figure it out. So we will do a little more of this on Wednesday.